Hello everyone and welcome to our channel CodeChef. Today we'll be solving the problem atoms in the lab. Let's look at the problem statement. Here it's given that initially there are n atoms in the lab, and starting from now when time equal to 0, after each second every atom will break into k atoms of the same type. They don't want the number of atoms to exceed m, so they have to decide to stop the reaction at some time equal to t, and we need to help find this value of capital T. Let's make this clear with some sample cases. Here there are two sample cases, and the first sample case value of n is 2, which means that initially at time equal to 0 what you have is 2 atoms. Then you have k is 2, which means that at every second each atom will split into k different atoms of the same type. So at t equal to 1, this atom will split into k different atoms of the same type, which is 2 atoms, and this atom will also split into k different atoms of the same type. That is why at time t equal to 1 you will end up having 4 atoms totally. Initially at t equal to 0 you had 2. Now when you continue this reaction at time equal to 2, this atom will split into 2, this atom will split into k, that is 2, this atom will split into 2, and this atom will split into 2. So you'll end up having 8 atoms. However, we need to find out time t equal to t to stop the reaction. We will stop the reaction at time t equal to 1. Why? Because if you allow the reaction to proceed, you see that the number of atoms you get here is 8, which is greater than m. The value of m is basically 7 here. Since if we continue the reaction, we get a number greater than m, we have to stop the reaction at time t equal to 1. That is why the output is 1. Also, if you notice something, at time t equal to 0, you started out with 2 atoms, that is n atoms. Now at time t equal to 1, you have n into k atoms. Now at time t equal to 2, you have n into k atoms. N into k atoms, that's what you have basically. So I hope you have like a relation forming here. Initially you had 2 atoms, then you had 2 into 2 atoms, then you had 2 into 2 into 2 atoms. Now if you check for the second test case where you have n is 2, k is 2, and m is 8 now. The only difference in this test case is m is 8. So initially at t equal to 0 you have 2 atoms. Now at t equal to 1, this atom splits into k different atoms of the same type, this atom splits into k atoms of the same type. So now you have 4 now. Now at t equal to 2, what happens? Now this atom splits into 2 atoms, this atom splits into 2, this atom splits into 2, and this atom splits into 2. Now you have 8 atoms here. Initially you had 2, then you had 4, now you have 8. Now if you allow this reaction to proceed for time t equal to 3, you will end up having 16 atoms by the same relation, because each of these atoms will end up splitting twice. So you will end up having 16 atoms. Now where to stop the reaction? For that we need to look at the value of m. The value of m is given to be 8. So that means at any point of time, as long as we have less than equal to 8 atoms, we can allow that time reaction to proceed. For example, at time t equal to 2, what is the number of atoms you have? 8. This 8 is less than equal to m. So it's valid, we can allow this. However, if you allow it for t equal to 3, you end up getting 16 atoms, that is greater than m. This should not be allowed. So we'll stop the reaction at time t equal to 2 in this case. So I hope this approach is clear. Now let's look at the approach to this problem. What we initially have is n equal to 2, k equal to 2, and m equal to 8. Let's take this example. At time t equal to 0, you have 2 atoms here. So what if there was a way we could find out the number of atoms you will end up with at time t equal to 1 before allowing that reaction? We know that the criteria for allowing a reaction is that if the total number of resultant atoms you end up with is less than equal to m, you can allow that reaction. Whenever this is not satisfied, that is, you get a reaction where the total resultant elements are greater than m, you immediately break out. So is there a way we can do that? What we'll do is, we will do while n into k is less than equal to m. Why are we doing this? Let's say initially you have n atoms. You know that if you allow a reaction to happen, the resultant total number of atoms what you get is n into k. And this will be your new value of n for further iterations. For example, if you allow this reaction at time t equal to 1 to happen, the number of atoms you will end up with is basically 4. That is n into k. And this is now your new value of n for further iterations. I hope this is clear. So what we're going to do is, if the value of n into k is less than equal to m, it means that this is a safe reaction to allow. So we will allow the reaction and we'll do count equal to count plus 1. And we'll do n equal to n into k, because a new value of n should be updated to n into k for further iterations. We have count equal to 0 outside. So how does this work for this example? Now initially we have n equal to 2 and k equal to 2. We check if 2 into 2 is less than equal to m, that is 8. Since 2 into 2 is less than equal to 8, we say that this reaction is safe to allow, and will allow this reaction and will increment the value of count by 1, and will say the new value of n is now n into k, that is 4, which means that the new value of n is now 4. Then what happens is we again go into this while loop and you will check if n into k is less than equal to m. So a new value of n became 4 and you will check if 4 into 2 is less than equal to 8. Since 4 into 2 is less than equal to 8, we can allow this reaction at time t equal to 2. That basically ends up having 8 atoms. Why is it possible to allow this reaction at time t equal to 2? Because the resultant atoms you end up with is less than equal to m. So again, you allow this reaction to happen because n into k is less than equal to m. Since this is an allowable reaction, you'll increment the count to 2 and you'll set your new value of n to be 8. This is the total number of atoms after the reaction at time t equal to 2. Then again you'll go into the while loop and you will check if 8 into 2 is less than equal to m. Now you'll check if 16 is less than equal to 8. This condition is dissatisfied. That means it is not satisfied, which means that this while loop will come out and then you'll print count as your answer. Count is your answer and 2 is your answer. Because till time t equal to 2, the reaction proceeded smoothly and the total number of atoms at each stage was less than equal to m. Immediately when you went to t equal to 3, you got total number of atoms as 16, which means that you will not allow this reaction and your output will be 2. That is count. So I hope this is clear. Now let's look at a few mistakes to avoid. I took this submission from the submissions page, and what they do is they have a while true here and we check here inside the loop if n into k at any stage is greater than m, we immediately break out. This is another way of writing the same code. Instead of having while n into k less than equal to m, they have a while infinity loop, and then if n into k is greater than m at any stage, you break out of the loop and print count as your answer. Otherwise, if this condition is not satisfied, what does this mean? This means that your value of n into k is less than equal to m, like we just discussed. So we will allow that reaction, increment the count and set the new value of n as n into k. This is all that they're doing, and they print count. Now this gives a WA surprisingly. Why is that the case? Because of the constraints. Let's say the value of n is something like 10 to the power of 12 and the value of k is 10 to the power of 12. When this happens, you know that when you check this condition in C++, n into k and both are long integers, when you do 10 to the power of 12 into 10 to the power of 12, what you get is 10 to the power of 24. But this does not fit the bounds of long int, which approximately I think 10 to the power of 18. So a better way to solve this problem and to avoid the constraints of overshooting the range of long int, in C++ we can do something like this. We typecast the value of n to double and we typecast the value of k to double. We know that the value of m is within the range of long int because m's value at max can go up to 10 to the power of 18 given the problem constraints. By typecasting the value of n to double and by typecasting the value of k to double, since the range of double is much larger than the range of long int, we can bypass this sort of input where if you have 10 to the power of 12 and 10 to the power of 12, it is possible to still check if it is greater and break out. So I hope this is clear. Now let's look at the Python code for this problem. What we do is we take the number of test cases as input, and then for every test case we take n, k and m as input. And how do we take this as input is we take the input, we split it by the default delimiter, which is space, and then we map all of these to integer. We have variable count equal to 0 and we check each time if n into k less than equal to m. This means that we can allow the reaction to happen and still have the total number of resultant atoms less than equal to m, so it is the safe reaction to allow. We increment the value of count by 1 and we set the new value of n to be n into k. At the end of the while loop iterations, the count will store the time t at which you have to stop the reaction, so we output it. As you saw, we got an AC in Python. In Python, we do not have to worry about the constraints on integers because int data type and int in Python can store large values. Now what we have is in C++. What we do in C++ is we have n, k and m. And then we input n, k and m for every test case and we have variable count is equal to 0. We do a little different than in C++ where we have an while true here and then we check each time if n into k is greater than m. If at any point n into k is greater than m, it means that that is a time at which we have to stop the reaction because allowing that reaction ends up having a resultant number of atoms greater than m. So at any point if n into k greater than m, immediately break out. Otherwise, if this is not satisfied, it means that you can allow the reaction. So increment the count by 1 and do n equal to n into k. Now remember to typecast this to double if you take the input as long int because n into k sometimes might exceed the range of long int. So I typecast this to double. And at the end, we know that the time to stop the reaction is stored in count. So we output count. As we see, we get an AC in C++. Hey guys, that was it. Thank you so much for watching this video, and if you haven't yet done this, this is a gentle reminder to hit that subscribe button. If you're interested in competitive programming and data structures, this channel is a one-stop solution for you. See you in the next video. Bye.